There we go. You probably can hear me now. Technical issues, and the technical issue was the user not doing user good stuff, you know? Okay. So today I wanted to do something a little bit different to kind of talk more about tech stuff, and I'm going to talk about how to subnet. So subnetting is the aspect of taking a network, which is what used in between a router to determine how addresses move around instead of a network. I'm not going to get into details of how that actually individually works, and that'll probably be a different video and a different live stream. But today I'm just going to talk about how do we subnet, and specifically like what methods we can use to figure out address schemes. And with that, we kind of need to know a couple of things right off the bat. And that's kind of like, what are we working with? And this idea of like private and public and then class ranges. So one of the nice things today, you're going to get a lot of whiteboard. You're going to see Ryan draw pictures, which, to be honest with you, isn't my greatest thing in the world, but we're going to power through it. Okay, I like the placement there. All right. So to start out with, an IP address is an association of ones and zeros made in a form that our human brains can understand what's going on with it. A computer does not see it in this way. Now, we need to understand that just a little bit here, and then we can kind of start building out what this means and how we actually interact with this. Okay. Get my jollying tablet in place. You're going to get to see the side of me for the most part today. Okay. Whoop. Mike, stay in place. Stay in place, Mike. Okay. Be a good Mike. Mike. Okay. Behave, Mike. Okay. So an IPV4 address is made up of 4 octets. Octet meaning 8. So there's 8 ones and zeros situated with each possible octet. Okay. So if we were to have 4 octets, we would have 1, 2, 3, 4. Okay. So with these 4 octets, there we go. This is where we can start getting to IP addresses. So the numbering for each of these goes exactly the same no matter which one we're in. But if we wanted to figure out what this number is, starting from 0, 1, 2, 4, 8, 16, 32, 64, 128. So 1, 2, 3, 4, 5, 6, 7, 8. Now, I'm going to go ahead and erase the 0 because we're not talking about how to add here. These are objects. Okay? We need to make sure that we're stipulating that. These are objects. Each one of these individual ones that are sitting here right now is a thing that can be used. It's not a counting measure. A 0 in what we're about to do is an object. So when we say between 0 and 255, we need 256. I shouldn't say need. We have ourselves 256 possible names that we can give these IP addresses for that specific octet. Now, as we move left, obviously we can keep on doubling that, and I'll talk about that here in a second. So let's go ahead and get those gone. Delete that little figurine there. Okay. And let's draw this better on the bottom. That way I can get a little bit clearer picture for us. So 1, 2, 4, 8, 16, 32, 64, 128. Okay. So those directly correspond to the positions that we're going to see up and above. And with these 8 numbers, we can determine any IPv4 address that's in that octet. Okay? So a 11111. So if we were to have all ones, in this case, all positions are filled. So we would have 255, which means all 256 objects are in use when we just talk about subnetting. Okay. But how did I get there? How did I get there? All right. Let's do a little bit of math. And you get to see how bad Ryan does math here, okay? So 128, which is always going to be our 8th spot. So I'm going to put little numbers underneath these here for a second. Okay. You're going to notice I am working from the right to the left when I'm writing these outwards. The data on these go right to left when we're thinking about how this calculation works. Actually, sorry, let me repeat what I said. We are going to do our calculations taking into consideration that the farthest right is going to be our lowest number and the farthest left is our highest number. Okay, so if that very first one, that 8th position, is 128, and then if we have 7 on as 64, because they're halving it each time and doubling it going the other direction. I'll talk about that more in a second. So let's do the math on this here really quickly. So that's a 2, carry the 1, 192. Okay. So 128, 64, 32, 16, 8, 4, 2, 1. All right, so let's add 32 to that. So that's a 4. 3 plus 9 is a 2. Carry the 1. 224. 224. Now we're on the 16. 0. Carry the 1. 240. 240 plus now the 8. 248. 248 plus the 4. 252 plus the 2, 254, and plus the 1 equals 255. All right, so we can see the math follows through. The math makes the 255, okay? All right, so another thing that we have to look at is this is doubling each time. So as I go right to left, and if I'm adding digits to the right, I am doubling what I'm capable of doing. Sorry, my dyslexia hit me there for a second. 32, 64, 128. Now, but if I think about this going the other direction, I'm halving it. So 128, 64 is half of 128, 32 is half of 64, 16 is half of 32, blah, 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 blah. So this is halving. This is doubling. Okay. Delete that. Delete that. All right. So we have a address. Let's give ourselves a 1010101. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if we want to figure out what this means in what we're going to call dotted decimal. So right now we're just dealing in binary. We're going to go deal with dotted decimal. So we need to figure out what these numbers mean when they correspond to those positions. So 128, 32, 8, and 2. That's the math that we need to do here. So 8 plus 2, that's 10. 10 plus 32, that's 42. So leaving us with 128 plus 42. So 0, carry the 1. 1 plus 2 is 3. 3 plus 4 is 7. So 1010101 is 170 in dotted decimal, which is our regular number. Which means this is the 171st place of an object. Because remember, 0 is our first object. So this is the 171st place of an object, and it is named number 170. All right. So that's kind of how IPs work. Now, let's go look at this and how this works with subnetting. There we go. Hey, I said delete. All right. So subnetting. So subnetting is the aspect of taking a single network and breaking it into smaller pieces. This is where we need to start being aware of IP classes and then IP public and private addresses, because these are going to what you're going to end up using for these type of things. All right, so let's start with IP classes. So you have A, B, C, D, and E addresses, okay? So let me look at something really quickly. I don't want to give bad information. Because it has been a little bit since I've looked at this myself. Yeah, okay. I'm glad I did. Looking at right, 126. Now you're going to notice here I'm not going to use 127 for anything. And I'll talk about why here as we kind of progress. So this goes to 128 through 191.255. Class C starts out with that 192 through 223.255.255. And then we have 224 going to 239.255.255. And then this one is 240 through 255, 255, 255, 191, 255, 255. Okay. So these are the classes of IP addresses. Class A, B, C, D, and E. Okay. First off, you are not ever going to use Class E. This is what we call reserve IP addresses. No octet 1 of an IP address is going to start with a 240. Not going to happen. All right. Then you have the next one, Class D, multicast addresses. So you should not be seeing multi-class addresses delving too much into like public and private addressing, and I'll talk about those here in a second. But these are how we can kind of connect to multiple devices at the same time, and it's really kind of useful when we're sending information our data from one place to another thing in big forms. And I'm talking more than like a packet. I'm talking like if we want to send like an entire file, multicast to multiple locations type of things. Okay. So we're not going to see a lot of class D, but we are going to see a lot of class A, B, or C addresses. Now, if you notice, I've excluded 127, 127, 000 to 127, 255, 255, 255. This whole range right there is just for loopback. Yeah, you can be able to come watch it later. This is all on. This is just on my YouTube channel. It will be in the networking playlist. So we're not going to worry about anything on there. The funny thing about loopback is they gave it a huge /8 network size, but we only ever use 127.0.0.1 for dealing with this. Everything else is just regular IP addresses. Okay. So we class A, class B, class C. Those are the addressing that we're going to use and where we're going to keep most things. Okay. Which leads us into the type of addressing you're going to see in class A and class Bs. I might have to turn the shape thing off on here because it's getting a little aggravating. Come on. Let me see if I can turn the shape thing off because this is getting an object snapping. Ink the shape. Okay. Fine. Okay, I'll create a new one. All right. So let's just I want to do. So on A, B, and C, we only use the following things for these. This goes into this address category, private versus public. So these are private addresses that I'm about to put on here. And this is what you're going to see being used internally. All right. So for class A addresses, anything within 10.0.0.1 to 10.255, 255, 255. For B, 172.16.0.0 through 172.16. Oh, sorry, that's not 16. 31.255.255. And then this one here is pretty straightforward. This is 192.168.0.0 through 255. Okay, so on that 192.168.1, this is only you're only going to be using the 192.168 on a private IP address. The 00 can be changed out. So if we make any changes on there, we can make that a 0, 1, 2, all the way up to 255. And then our network itself is going to be down here on this other 0. But I'll kind of show that because this is network A and network C are the most commonly used IP addresses. Now, these are private ones. These are used internal networks. So your home network is using this. Your Comcast is using the public IP address. So anything that's not shown on here is going to be a public-facing IP address, meaning that it is uniquely identifiable across the world. And for the most part, public IP addresses are sold out. You're not going to find them for available use anywhere in the world. They are. That just is what it is. All right. But you can use any of these internal addresses. I'm pretty sure most of my networks are done with either a 10 network or a 192 network. Surprisingly, you don't see a lot of Class B network in use, but And you could create one if you're building your own networks. All right, so now that we've seen what the classes are, let's kind of do some breaking up of some stuff. So I'm going to give us a network, and then we're going to talk about subnetting outwards. So I like to work with the tins because anything that we apply here in the tins can work in any other network. All right, so if we have a 10.0.0.0 network, this originates from what we call a class, not a class A, but a 8 size network, meaning that these 3 ones, the 3 octets on the right of the 10, are all open to be condensed and made into smaller networks. So a 10.0.0.0 /8 is the largest you possibly get, which has millions upon millions of possible addresses. And really, that's what you're going to see in corporate. You're going to see a lot of 10 networks. And a lot of people who are going to be building their own, they're probably going to stay within that 10 because it allows for the wonderful thing called growth. The more that you're able to grow, the better everything will be, which is part of the reason why we're moving to IPv6, because you can give a name to every star in the galaxy, every star in the sky, every granule of sand on the beach, and you'll still have enough IP addresses left. That's the theory. I give it 2 decades, and it's all going to be gone. All right. So if I have 10.0.0.0 and I want to make that a smaller network, this is what we call subnetting. Because we already have a network, now we're going to take that network and make it smaller. So the first network I'm going to build out of this is I'm going to build a /24 network. And a /24 network is probably the easiest for us to create. So if we were to start out with that 10.0.0 and I want to create a /24 right from the get-go, I could build a whole bunch of /24 networks fairly easy without having to do a lot of math. Okay. And if you're noticing, I'm only changing octet number 3. All right. Anything 24 and above is going to be in octet. We're going to start out in octet number 3. All right. Let's think about this here very quickly. All right. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So a /8 happens right there. All right. So that 10, because it's in that first spot, that first octet, and a /8 represents that those 8 ones, those 8 positions, correspond to where that 10 was. And a 10 is, let's see here, 1, 2, 4, 8, 0. So that would be the IP address of 1. It would be 000011010 with a subnet of 255.255.255. I'm sorry, 255. All ones. Okay. So where I showed you /24 was, so 8 plus 8 plus 8. So if you look up 8 times 3, 24. Specifically, that spot right there is the 24th place of a subnet or an IP address. Okay? So if I were to create a 10.0.0/24 network, this would actually read as 0.00010.000000000. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if we had created that 10.0.0/24, everything to the left of that is our network mask. Okay? That's our network because of where that 24 slot was. If I would have turned this into a 25, I would go 1 to the right. If I was going to turn this into a 23, I'd go 1 to the left. which would then change where this marker was at. So that's the network portion of that. And then if we overcompass this with ones, that represents the subnet portion of it, because a subnet just represents, we represent subnets by all ones. This would be 255, 255, 255.0, okay? And this would be 10.000. Okay, so anything above the 24, you're not going to ever touch that number. But if I said, okay, let's give ourselves a 16, okay? A 16 would cut us off there. And then, because that's the 16th place, so this would be like 10.0.0.0/16. We would start changing our networks there. And then anything on the right of that is all potential host address. So to the left side, network. To the right side, hosts. Okay. So this is the essence of it, okay? Most people, when they start out subnetting, we're going to start out sub 24. So we're only going to deal with this last network, and that's where I'm going to kind of focus kind of the rest of this conversation on. Okay. So if we have, oops, that was supposed to be an eraser. Yeah, sure, let's erase everything. All right, if we have a /24, 1, 2, 3, 4, 5, 6, 7, 8. All right. On a /24, we have identified that everything to the left, those three other octets, so 10.0.0, that's not changing. So that's the network ID portion of this. And everything to the right of this is hosts. Okay. So let's say we want to go smaller. And this is really where our first terms of like learning how to subnet really come into play. All right. Every time we move to the right, we're adding 1 to 24, right? So this is 25th spot, 26th, 27th, 28th, 29th, 30th, 31, 32. Remember what I said, directional. So every time we move to the right, we are going to half our network. Okay. A chart. Get off there. All right. A /24 is equal to 256 possible IP addresses, which equates to 254 possible IP addresses. Okay. So if I had a 10.0.0.0, this 0 is my net ID, and then 255, sorry, 10, let me draw this in a better way. 10.0.0.255. This is my broadcast ID. Okay. So, how do I know what if a number is available in there? So anywhere between those two numbers. So 0 is not usable because that's our network ID. That's how we identify what network we're on. 255 is a number that represents that we are allowed to talk. If we talk to 255, we're able to talk to every single IP address in the network. Okay. So for use, we have everything between 1 and 254 available to us. So on this scenario, a /24 is a 10.0.0.0. It ends at 10.0.0.255. That's 256 IP addresses in use. It has 254 usable IP addresses. So, term I have not used yet. CIDR. Oh, come on. Back. CIDR. CIDR. That is what the slash is. You'll currently feel like, what's the slash network? What's the CIDR network? Okay. Total IP addresses. Usable IP addresses. Okay. So if I start breaking this down, 25, and you're going to notice a pattern here. Then if I go a 26, a 27, a 28, a 29, a 30. I might not be able to draw anymore. 4, 2. That's basically as small as we can get. When it comes to subnetting, you're not going to purposely subnet into a 31 or a 32. You will see a 32 in use, but you only see a 32 use in what we call a routing table, which is normally only seen on a router or in some of the advanced features of a server. But for our purposes, 30 is going to be the lowest we're normally going to go, because that leaves us 2 addresses. There is no point whatsoever to go below 2 addresses, and for following the scheme, I was not going to get 2 addresses. My next one would have been 0. But if you look here, take a look. So 1, 2, 4, 8, 16, 32, 64, 128, 256. That same pattern that we saw a little bit ago. Did I keep a copy of it up? No, I didn't. Here, I'll create it really quickly again. So that exact same pattern that we were using to determine is also used here. Okay. So as you can see, we have it's a pattern. It's showing up over and over again, and you're going to see this pattern constantly over and over and over again. It's going to be something that the more you subnet, the more often you're just going to see this natural pattern. And what this is called is base 2 math. And you can do all this based upon base 2 math. But we're going to kind of ignore getting into the math side. I'm going to show you a couple little tricks to, if you don't feel comfortable with the math, these are some tricks that you can be able to use to kind of get around doing the math. But you're going to need to have a chart like this readily available. And this is kind of a common subnetting chart that you'd be able to find. And this is something that if you're wanting to learn about subnetting, that you probably want to sit down on a piece of paper and recreate this, or create this on a piece of paper or a sticky note that you can be able to refer back to. Okay. So how am I going to take a chart like that and use that into something meaningful? Okay. So let's first start off with saying I want to split my network in half. And I'm actually going to give us a more complicated network this time. So I'm going to give us 10.7.8.0. And I'm going to say I want you to split this network in half. Okay. So we know a /24 again has 256 total IPs. And if we remember backward, the /25 had 128 possible IPs. So the kicker that most people have The first problem that they have is realizing that if I'm going to take a /24 network and divide it in half in any way whatsoever, well, what's my network ID of the first network? Well, it's always going to be 0. If your initial network started with a 0, it's going to be a 0. Whatever your network started with, that's going to be your first of your brand new networks. And as I said, I want to split this in half. So 25 was half of 24, which meant 128. Remember that 128. So 10.7.8.128/25. Okay? So that's kind of the direction we're taking that in. Give me a second here. Something was going off, and I don't know where it was. Oh, well. Okay. All right, but how can I determine if something is in there? Which network does it belong in? Okay, there's 2 ways that we can go about doing this. So we're going to use that 0 and that 128. Okay. So a 0 network is A 128 is 1 ... All right. New word, new phrase. Interesting octet. All right. Interesting octet refers to where was the last 1 at. Do we have a 1 in that octet, and where does it change from being a 1 to a 0? So on this network, we on the 0 and a /25, this spot is where things are possibly going to change at, because everything up to this one was 1.1, 1.1.1.1.1. Let me show you this in a little bit better manner. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. .1, 0, 0, 0, 0, 0. Okay, that's the subnet laid out in 1s and 0s. Okay. Now, this is our interesting octet, because this is where our subnet is saying that, right? So this spot has 2 possible options. It only has on and off. So if we were to look at, remember this was 10, oh, I don't remember what it was. What was it? 10.7.8.0. Okay. 10.7.8. All right. And we weren't sure which network something was going to fall into. So I'm just going to put a number out there. I'm going to go 154. All right. So 1 is 128. Remember, we've gone over that. So 128, 128. That's what that 1 represents. A quick and dirty way. Does 154 go into 128 with nothing left over? In this case, no. There's going to be left over. There's going to be about, bad math. Let's just do regular math, Ryan. All right. So 4 minus 8 is 8. Carry that one. So 4, 28. There'd be 28 extra. So this means that a 154 has to be within that network. Okay. There's another way for us to potentially do that without doing the harder math. This one we just have to know where the splits are at. Okay. So we know 0 was the start. 255 was the end. So we know for a fact that's the /24. All right. But a /25 was half that number, right? 128. All right. So we know 128 was the start of the second network. And now 255 is the broadcast of the second network. So all we have to remember is when we're splitting, we still have to have a broadcast address for the first network. It's just -1, 127. All right. So now, without doing a whole heck of a lot of math, we now know anything between the 0 and the 127 is on network 1. Anything between the 128 and the 255 is on network 2. And if you're really not 100% sure about things, you can do it this way. 1 through 126. That's my usable. 129 through 254. That's my usable. Pretty straightforward way. Really nice, simple way to be able to visualize, especially if you're a visual person. All you need to do is kind of refer back to that little chart we did a couple minutes ago. Let's bring it back up. So basically, we refer back to this chart and remember, whatever our network is, that's how many breaks we need into it. So I'm going to do something with 32 this time. Okay. So this time I'm going to build the network in a different direction. All right. So I have a 0 and I'm saying, okay, I want to break this into 32 total IP addresses per network. Okay. Well, we know 32 is the start point. Then if we keep on doing 0 plus 32 is 32. 32 plus 32 is 64. 64 plus 32 is 96. Plus another 32, 128. Plus another 32, we would have... Can't do math. 0 carry the 1. 160. Yeah, that's right. 160. Then add another 32. 192. And then we add another 32. I can't do math. So 4. 224. Okay. 224. And then 256. But obviously 256 isn't real because that'd be going into a different network. It'd be 255 because that's the broadcast of that one. So what do we know? Well, we know for a fact that this would be a network. Then we just -1 here. 2, 2, 3. -1, 1, 9, 6. I did bad math. I did very bad math. Hold on 1 second here. 160 plus 32. Oh, that's supposed to be a 2. 191, 128 through 159, 96 through 127, 95, 63, 31. Okay. So that's another way that we can go about doing it. Then all we have to do is add that primary digit up throughout it all. And then it's just 1 through 30, 33 through 62, 65 through 94, and so on. And that will tell me where every possible address in this network could be at. And it's a good way to lay it out. There's a really, really good way and simple way to kind of lay it out where things could possibly sit at. Now, if you're a math person and you like doing the math and you're kind of like, oh, I want to figure out how to do this math. All right, let's go back and look at this. Where'd it go? Okay, let's look at this chart again really quickly. And then we're going to kind of do this from a slightly different perspective. All right, a 32 is a /27. All right, so we need to make sure we're having 27 ones, which is only 3 additional ones. Okay. So if we have 1, 1, 1, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is back at the binary. So we can figure this whole thing out just by looking at the binary if we want to. So 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. Each one of these ones represents an exact place for the network ID to be at. Okay? So if I have no ones, that means all zeros, which is a 0. Right. And then if we start going towards things, if we just have 1 there, so if that one's on and those 2 are zeros, if we do 0, 1, 0, zero, 0, 1. Okay. Is there a way I can move this? Funny thing is, I know you can do it. I just don't remember how. List, grid view, no. Being image. Oh, I don't want to type. Okay. Oh, regardless. If I were to go like that, so that's 128 plus 64, 224. So you're seeing how, depending on the combinations of this that we use, that's how we can get the exact network IDs. And then once you get the network IDs, remember, it's just, we already determined 32 is our max IP addresses. We can just do plus 32 minus 1. Remember, the minus 1 is to bring us back 1 to get that broadcast address. So in this case, 128 plus 32, 128 plus 32, 0, carry the 1, 160. So this would actually be 128 through 159. We just got to minus that 1. Okay. So what about if we go... okay. So we have a couple of different ways that we can split networks. And there's a methodology that we have to follow. 1, biggest network first. Biggest network first. That always has to be true. Okay. If we don't do biggest network first and we do smallest network first, then it is possible for us to go beyond our possible allocation. Okay. 2, always have enough usable IP addresses to cover what you're actually trying to do. 3, plan for growth. Okay. There are a couple times when we don't plan for growth. So this is a router connected to another router. Okay. We call this a point-to-point connection because there's only 2 possible locations for IP addresses to be connected to. And normally if you have a point-to-point connection, one of these routers is connected to a switch, and there's a whole bunch of other... Actually, both these routers are connected to switches at some point in time. And there's a whole bunch of other network coming off of here, okay? And that's a whole different subnet that can be used. A point-to-point's only ever going to use 2 IP addresses, so we only need a /30 for a point-to-point connection. Now, depending on, like, if you're going to, depending on certification test you're after or other things, They will use other networks for a point-to-point, but there's just really not that much of a use in real production unless you have a cause for it. And for kind of an introduction into this, there isn't a cause for this at this point in time. All right. So anything else after that, we want to only use. We want to use what's appropriate for that network. We want to have the ability to potentially grow into that network, and we have to make sure that we have enough to make sure it's usable in that network. So a common problem. Let's say net 1, 2, and 3. Let's say we're going to give net 3 2 possible ones. Then I want 61 possible ones. Then I want 136 addresses. Okay, so we need to figure out a network that's appropriate for this. So what I'm doing here is what we call variable length subnet mask. Right? The networking that we were looking at before with subnetting, that was all kind of built upon each other. We're just using the same Lego box to split it up type of thing. Like I have a 32 plus a 32 plus a 32 plus a 32, or a 64 and a 64 and a 64 and a 64. We're just using the same subnet for all of them. Guess what? We don't really use that. We use that, but we seldom use that. We're going to use variable length more often. So we need to figure out 136, a network for 136, a network for 61, and a network for 2. Well, I already gave us a network for 2. This is a /30. A 61, so realistically a /28 would probably work here. The problem I gave was not possible to do, and keep it all within a /24. So a 28 would be okay here because the 28 allows for 62 possible ones. It allows us for one address of growth, which is fine. 126, we can use a /25. Oh my god, I'm very dyslexic right now. 26. There we go. So we could use a 25, a 26, and a 30 to make to cover these possible addresses. Okay. So a 25 goes from 0 through 127. So that's the /25. The 28 only deals. I really am dyslexic tonight. Wow. Numbers are not complicated. They're just giving me a bad night. Okay. So 128 for our /26. We're going to use 64 possible addresses, but we're only going to, so we can go 128 plus 63. So that's going to carry a 1, 191. Which means our third network is a 192. And we only need to deal with 4 possible addresses, so 190. 2, 3, 4, 5. Okay, so this is variable length subnet masking. This is where we've taken a network, we've broken that network down to variable sizes to match what the network actually is going to be using it for. So we need a 25, a 26, and a 30. Okay. And that's kind of what variable length subnet masking is. So kind of takeaways. The big things that you need to remember is a chart like what you're about this here is extremely important to make. Until you get to that point in time where you just know how to interact with it, no matter what. Okay, especially when you're dealing with sub-24. When you go into to above 24, our numbers get bigger, but the same concepts apply. We're just talking about more numbers. Okay. So if we wanted to do a /23. slash 23 means that's the 23rd digit, which means now the third octet is interesting. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 0. Okay. So that doesn't matter. There's our entering octet. And then we can just do the same math that we were doing before to be able to figure out how many possible networks that we have. The only thing we have to take into consideration now is that, so remember, this way was, yeah, bigger numbers, more problems. If we were taking this number to the right and decreasing it, we'd be halving the number of networks. But if we're going to the left, we are doubling the number of networks, or number of IP addresses. So if 256 was what we had at 24, if we double that, we're going to get 512 for our 23. If I move this one more network, I would get a 1024, and then a 2048. So the more times, the more to the left we move, the more doubling that we keep on doing over that base of a 24. So that's a big thing you have to remember when you start doing bigger size networks, is just dealing with more doubling of the network size. Okay. Now, would you use a 23, 24, a 23, 25, a 22, a 21? Yes, it is entirely possible to see business size networks up in that realm, because we were talking about a couple hundred devices, which is theoretically possible. On most of the small networks that I've ran and managed myself, we're talking like maybe 50, 60 users. I still had between 200 or 300 possible IP addresses running at any point in time. And when you start talking about big corporations, we could be talking not only thousands, but tens of thousands or more, because every single node that requires an IP address needs an IP address. And there's lots of things that needs IP addresses. It's not just the computer. Anything that's intelligent on the network has to have a IP address. I'm fairly certain probably if I were to actually count all the objects on my network that actually were drawing connection at the same time, I'd probably range between 70 or 80 objects just in my house. That's all the things that are possibly connected to the network at the exact same time. They don't all connect at the same time, though. But in a business, it's not the what ifs. If they can connect, then they get a network, they get an IP address, and we move forward. Okay. All right, so that's the simple version of IPv4. Nice thing is you should be able to watch this over again if you need to. You can just watch it over. But if you have any questions or anything, I'll kind of stick around here for another minute or two. And if the chat wants to ask me anything, if not, yeah, that's totally fine. But that's the essence of subnetting. It's pretty straightforward once you get over the nuances of it. There's a whole bunch of ways that you can go about figuring out the problems on it. Doing that little like bubble thing that I was showing there, where you're kind of breaking things up into different areas. I really like that one for people who are new to subnetting. But if you're good at the subnetting, then you can just straight up move into looking at the binary of it. Doing the binary portion of it is the quickest. And once you kind of embrace that, subnetting becomes extraordinarily simple. So, are you going to use subnetting in an IT job? Yes. Yes, you are. Now, maybe not in the way or premise that you might be thinking. So you don't think you understand the ways of backwards, but I get the multiple additions. So when you mean backwards, do you mean like the fact that we start from the right when we're adding things up versus when it leaves to the left? How do I explain this? So this has more to do with our human brains and the way that it actually works. let's think like a machine for a second. A router, a switch, a computer, a laptop, a desktop, anything at all that's dealing with the networking capability of it. Okay. When the device is looking at it, it is going to look at that first. It's reading it in this direction. Okay. And it's not reading just the IP address. It's reading every single bit of data in that manner. And what it's looking for when it goes through these routers and switches is those subnetting markers. So we're looking for what is the corresponding subnet matched to that network, especially when it goes through a router or switch, because that's how it's determining where something is going to. So you would have your IP address sitting in front of it. So let me put a kind of a rudimentary IP address here first. So what was it before? 0.0000101.0.000.0.110.0.0.110 Okay. My quick math says that this should be 10, 7, 8, 120, 191, 192. All right. So the way a router and a switch reads an object. So the IP address comes through like this, and then immediately following it, okay, so think of this as all one long stretch of ones and zeros right now, okay? So when an object is sitting here reading this, and this is even before it gets to the data, the actual datum in the grams that are sitting in there that actually make up the content of the packet that's going through there, it reads the IP address. And then it reads the subnet. So it reads all the way up to there. And when a router looks through that, a router does not care about those last 7 digits in this case. So it does not care about the last 7 digits that are on the IP address. It just knows that you want to talk to somebody who is on that network. So where all those ones were at, the moment that's up to 0, it stops caring about those zeros. It's looking for where all these ones are at, okay? And then it pushes over to the switch. And the switch then is going to correspond, hey, I see you want this with that, with the MAC address. So the next thing that would actually be following this is a MAC address if the device knew what that MAC address was. Okay? Again, in ones and zeros. So it's reading it in this manner. It's going down the line, reading from left to right. Because if this was a /8 network, and let's say these were all zeros, it would read all this. It would read those 8 zeros and go, hey, I don't care about the rest of this anymore. I'm just going to look back at that first portion of it and say, oh, okay, you want to go here. I know where here is. I'm going to send it in this direction, and it's going to bypass the rest of that data. It's not going to even read it. It's going to move forward. But the problem is that our brains aren't computers. We have flesh in there, and our internal mechanisms for our brains to be able to figure out things do not work in the same mechanical method of electronic impulse going on and off. And that's what this is. This is an electronic impulse. This is power on, off, on, off, on, off, on, off, off, off. Okay. So when we sit there and we see 1 0 1 0 1 0 1 0, we had to have some basis behind trying to figure out the scale of these networks. So 1. 64, 32, 16, 8, 4, 2, and 1. Okay. So we needed something to be able to, for us to be able to understand when we kind of did math on this one, but we also wanted the devices to go through there and figure out this as much as possible. Guess what? I was showing a picture and I didn't bother to show it on the screen. My bad. All right, so I want to jump back to this one here a second ago. All right. So where all those negative, all those ones are at versus the ones, it's only looking at those corresponding portions of it. Okay. Loading. Okay. So the computer is reading it from that direction. 128 is the biggest possible number. So if the off-ramp situation, the situation that potentially could tell it, hey, this math is over with, stop calculating, as at the front portion, the left side of this. So here's our IP address, here's our subnet. If this is the portion on the computer that we're saying, hey, stop doing calculations, send the rest of the product, we want that as in the front, farthest in the front of our communication as possible. Because it takes time to read. It just does, right? I mean, it takes time for even on our own brains. If we look at a word or a picture of something, it takes a little bit of time for it to process. So if we're going to send traffic as quickly as possible to get to a location, we don't want that device to sit there and look through every possible digit before it's saying, hey, okay, I know where to send this. So if it can figure it out on the first number of the 8 to make that decision, then it doesn't need to read the other 7, which means faster traffic, which means data is moving at a quicker pace, which means that the router is not bogging down by having to calculate all these things getting to it. Now, obviously, the farther down we go on this, the more time that it's going to sit there and read it, because it has to think more. Then it has to look at what are routing tables. And again, when we look at these things, we look at them in plain English, in dotted decimal, but the device doesn't. It only sees things in ones and zeros. So if it has a routing table that's saying, hey, if you have this, send this out port 2, then that's all it needs to know. It saw this 1. It saw, hey, everything turned to the next node was a digit. I can ignore the rest of this. I look back at my routing table and say, hey, a 1 in that slot, and I'm supposed to ignore the rest of that, goes out this port, and then I forget about it. So from the computer aspect of it, this is the quickest possible way to get traffic to travel. And every electrical circuit dealing with data deals it in the same way. Ons and off, and we want things to be moving as quickly as humanly possible. But yes, I get it. Our brain doesn't work that way. Our brain sees this as not 128, 1, 2, 4, 8, 16, 32, 64, 128. Because we started our counting at 1, because that's how we were trained to start doing our counting ever since we were children. Same with the aspect of we were trained to do our counting as 1 plus 2 equals 3, right? Well, we never objects instead of numbers. So in this case, if we were to do 1 and 1, okay, that does equal 3. But if I were to go 1 and 0 equals 2. If I go 0, 1, it equals 1. Where we start when we start counting is kind of irrelevant in the big sense. It's just kind of how we were taught to deal with arithmetic. And like when we were children, we started learning to count at 1, 2, 3, 4, 5, 6, 7. And that's how we kind of determine things. But if we were to sit here and count objects, and I were to say, hey, this is object, this object name is 2, this object name is 4, and I go 4, 2, this is a name. This is a name. This is number 4. This number 4 is a very nice, happy pin. This is 2. 2 is a very nice, happy controller. We just have to get out of the idea that a number represents arithmetic in multiplication, and we're referring to it as an object. And once your brain makes that correlation, then it starts to make sense when we go back there and look at these things, that when a router looks at it and it sees like 10000 as the subnet, and it goes 1, oh, I already know the name of that one. I already know the street address that this is going down. Another popular way to explain IPv4 addressing is to think about how the mail system works and how IP addresses work. Not IP addresses, but how you get a piece of mail. So like another good example of this is if I wanted to get something to Seattle, Washington, and I lived in Houston, Texas. Okay. I'm Joe in Texas who lives at 123 Bob Street, and I want to mail something to Sarah at 345 Jane Street. Does the mail carrying system have any knowledge whatsoever of who Sarah is or who Joe is? They don't. They don't care. So when you mail something, the first thing that they're going to look at is zip code, and the first thing they're going to look at is those first couple of addresses. 982. 982 is a regional. So if you look at 98200, specifically 98. Sorry, 98 gets you to the geographical of the greater Seattle area. 2 should put you heading towards Seattle itself. So mail gets shipped to there. They have no idea where that is. They know where 98 is. It gets shipped in a truck heading towards 98. It gets to a facility that does 98. It looks at that third digit and says, okay, I know where 982 is. And then when you get into these last 2 digits, and a lot of times you'll see 4 more digits, 5555. So once it fills those 4 slots, that's identifying the actual post office box. The 5555 identifies the route. Now, again, this whole time from Joe to Sarah, nobody at the postal system knows who the heck Sarah is. They don't care. I mean, quite honestly, they have no reason to care. They were just told to send packet to Sarah. We get here on this route 5555. 5555 probably still doesn't know who Sarah is, but they know who 345 is. So they're going to go to this location. And at this location, you get into like, okay, I'm just going to mass drop it off there because the MAC address and everything matches. They still don't know who Sarah is. So that's why you can get a piece of mail in the mail, not addressed to you, but with the right address. So you can have mail that's sent to your address that's not addressed to you. The mail system isn't going to stop that. And the same thing works with IP addresses. It's the same premise behind this. That's why it reads left to right instead of right to left, because it's going to look at where does that location at, where's the next location, who knows who along the route. So think of these as routers. This guy here doesn't know this girl here at all. Has no contextual way of knowing who that is, except that it wants to send information to it. And this router, the only thing this router is aware of is that router. And then whatever's off this side of it. This router only knows here to here. This router only knows here to here, then here to here. They don't even know anything else about their world. That's it. And that's why when they look at those subnettings, they don't read the entire thing. There's no point. They only read enough to be able to send it to the next available location. Our brains, being humans, we want more data. We need more. We need to understand the rest of why we send something instead of just put it in the box and send it. Okay. So I hope that kind of explained that one. It's more of a subjective thing from how we view it versus how the device is actually doing with things. It's all about numbering and scheming, number schemes, and how it's interacting with one another, and being able to identify and move something forward as quickly as possible. Okay. Well, I'm not seeing any other questions. This video will live up. It'll be in my playlist called Networking. As I progress forward with doing this type of things, more things will start filling out there, and you'll find more of these little kind of how-to guides and stuff like that spread across things. So if you like this, thank you. If you want to share it to somebody else to be able to help them figure out how to do some of this stuff, go ahead and do so. All right. Remember, don't say goodbye before I put the screen in place, Ryan. All right, there we go. All right, thank you for watching. Bye.